All right, then let's get going. Good evening, everyone. Let's have a look. Hey, welcome, Jake. Oh gosh, it's happening again. My face isn't already. There you go. See, I thought for a second it was broken again, but then it turns out on the theme of cybersecurity, the best weapon of the best defense you can have is a bit of plastic just covering your camera. So that's probably the reason why I wasn't working. Good evening, Nick. Good evening, Manpreet. No, we have Prince as well, and others too, John. Others too, which likely will follow soon to come. So hope you're keeping well. Hope it's been another week that we can celebrate with lots of good things happening. Actually, within the Academy inside and out, I do have some good news that we will be talking about shortly. Without spoiling the broth or giving too much away, it's come to our attention that summer is always the lull. By the way, I want to say people go abroad, they do things, they have a life, and when we do have fewer numbers, we reduce numbers. We start to think about what we want to do and think about what's going to happen ahead. You've seen my face for a couple of weeks now, and that's because the kind of other side of the Academy is now getting busy working on other fresh ideas. One of the things that's being pitched about is bringing us together underneath one roof, and I'm thinking about building something called a jam. And if you've not heard of an AWS jam, it is essentially a way for us to collaborate and play together. Doing labs. So rather than us working in isolation, it's a way of gamifying this so that we work towards a common challenge and work and apply these challenges all at once. Much more information to come soon. There's a lot of things still need to to happen to make this right, but it is going to be hopefully happening soon. Okay, so that's one thing we will be looking at very shortly. And what we like to do is these sessions, keep them a bit alive. Welcome AJ, welcome Jake, welcome Sally Muhammad, and others too. Welcome as well. We want to keep things fresh and sort of look at other things outside of necessarily the cloud so much. So today we're going to have a discussion around cybersecurity, and again next week and later on we're going to talk about cybersecurity in the context of the web and the internet and some of the challenges that it brings up there. But today, I wanted to come back and focus mostly on cybersecurity as it relates to your machine, as it relates to your memory, as it relates to your computer, without necessarily being connected to the internet. So, well, before we do that though, what we need to do is first understand a little bit about your computer itself, your machine's infrastructure, so to speak. And the biggest question then to ask is, I guess at the outset, is, well, when we talk about systems memory, what do we mean by this? What is memory? This kind of term gets thrown around a lot, and it means a couple of different things, again, depending on who you ask, potentially. Let me throw that out to you as an open-ended discussion. What do you mean by your system memory? Well, this is definitely on AJ's domain, so I'm sure you've got some ideas to throw about there. So what comes to mind? If I can just get some ideas on the screen, or perhaps from a mood board. What do you think in terms of memory? All right, so if I'm using the word memory, what kind of image does that conjure up in mind? Definitely goes this one, RAM. It seems like we're swapping one for another. So what is RAM then? Potentially might mean your system's RAM, sure, or better known as random access memory. More on that in a second. I guess this is a rough translation of how much computing power does it have? How much can you do at one go? Definitely random access memory. How many things how many juggling balls can you juggle at once? And so we can talk about hard drive space in order to make your computer faster, somehow relating to speed of access. When we think about your hard drive and kind of the capacity that brings, as another example too of your system memory. And then for this, I guess we need to have another look under the hood then, so to speak, at what things like this means. For example, Intel inside usually. So if your Mac, your phone, your PC has this Intel inside logo inside, as a marketing slogan would go, then that means your computer has inside of it the CPU or the central processing unit of something that looks a bit like this. So this is a pretty small device, and it's not quite as big as this, obviously not drawn to scale. It wouldn't fit inside your actual computer if it was, but what you do see here is two sides of the CPU. And this is really just a metal case, a nice big printed logo on the front there. And then again, if you flip this around, it looks a bit like the wings of the Hubble telescope. This on the other side, which generally has a whole bunch of these golden pins on the front that actually interconnect and interweave to a device inside the computer. And then what the device actually is that motherboard too. So the motherboard, we'll see in a second, is usually a green bit of silicon. A circuit board, also known as, which is a big plastic or a big plastic-like material with a lot of lines running on the back and forth of it, and it often has these sockets inside of which, essentially just a bunch of tiny little holes there, so like this one, so that devices a bit like this can fit inside of that computer and actually have it clamp down upon something. So what does it mean though to be a CPU? Central Processing Unit. Again, well, the CPU is analogous to maybe the brain of the computer. It's the thing in the computer that does all the thinking, it does all the work, so to speak, and all the calculation. Now, what kind of thinking does it do? Well, usually you're putting things like numbers inside. Okay, so numbers 0 to 9 somehow going through. From one side and then coming out the other as being interpreted. And then we want to feed these maybe letters or numbers that represent letters. Maybe you want to perform some kind of maths on those letters, on those numbers. Perhaps you want to display them on screen. Perhaps you want to add or delete or process them in some shape or form. So all that a computer needs to do is all that thinking is this, and that happens on our behalf, okay? So that piece of compute inside the computer that does all the thinking is indeed this CPU inside. Now, as it turns out, like nowadays, CPUs are getting pretty fancy. They're getting pretty good, and inside of the CPU itself is generally what's known as a bunch of cores, so to speak. So you might have multiple cores inside of a computer. And a core really is what's doing all the work, in a way. It's the device inside of this device too, that actually itself is doing all the addition, all the subtraction, all the multiplication and division and other operations too, which from memory are being pulled from, essentially, saving information to memory. And so a CPU might actually have multiple cores. It might have 1 or 2 or 4 or even more cores, which means by translation, it can do 1 or 2 or 4 or however many more things it can do at the same time. And that's really good now because, nowadays, my Mac, my PC, my phone, if I double click on a bunch of different icons, I might be running multiple programs simultaneously. I might be talking to you over here, I might be working on my homework over there, I might be doing all sorts of things at the same time. And so if I have a lot of programs open at the same time, simultaneously, thanks to multiple cores inside of a CPU, each of those cores itself can then run a program in parallel. So maybe one of them is printing out to the screen, another one is printing out to a printer, one's playing back a video, whatever it's doing. Any number of those operations literally can be happening simultaneously in parallel. Now, moreover, as it turns out that the fanciest ones today, from Intel especially, they also support something that's also known as hyper-threading, which just means that you might not have only just one CPU or one core, but thanks to some technology built into the CPU itself, it will present itself to the computer, to the operating system, to the Windows, to the Mac, to whatever, more of those in a bit, as though it's actually more, as though it's actually 2 or 4 or more cores. And so again, thanks to this technology, can your computer now think it's got more computational power than it really has? It's kind of a lie to itself, and then allowing you to take advantage of downtime or slow running programs that you might still be able to do by running things simultaneously. But we're going to come back to that in just a bit, because alongside other parts of the components in this diagram here, we have this. So not all the devices have just a CPU connected to a motherboard. Again, more at that in a sec. Some devices instead actually have a CPU, and all of these things actually interconnected all at once. And these things are generally known as a system on a chip. Maybe some of you might even be able to recognize a pattern on screen that tell you what kind of chip this is. Indeed, it's a bit of a fruit. So some devices like this one, instead they have a CPU, which you can see here more or less in the middle, and these other things are all interconnected as one. These system on a chip, essentially things like, they're very popular in things like tablets or iPads or watches or games consoles or the like. And indeed this one here, which you pointed out, yes, a Raspberry Pi. It's a very small computer, which pretty much looks like this, again, without the plastic on top. Also not to scale, but actually I have one of these at home, they're really, really cool. This thing can actually fit in the palm of your hand, it's that small. And so this has, again, all of this is a green silicon board, generally green, and you'll see the very, very, very thin, fine lines running across the board. These traces, they interconnect all the chips, all the technology that's plugged into essentially one thing. And it also has, well, first of all, it's got no case. There's no plastic case on that protecting all the components. It really is just a raw piece of hardware or computer that technologies or technophiles like to build and kind of program with. Also to this, it has a whole bunch of these ports on the side, and we'll come back to them in a bit. Basically, a whole bunch of places where you get to connect other devices inside of. But these systems, they all come together on one single chip. That's what makes them what it is. And they can do many things beyond just the task of the CPU alone. Okay, but what else things? Aside from this, aside from the CPU, what you see on the screen, there's other components that also fit inside the computer that make it do the actual work. And so the most important one in today's discussion is that of memory, or random access memory, or RAM. And so random access memory physically looks a bit like this. Again, this is a chip that you might slot into your computer, essentially, specifically on a motherboard. Again, so a big greenish board, which all of your computer's components connect into. And so there's usually a little divot here, a plastic thing, a little bump, just to make sure you put it in the right way, instead of the other way, for instance. And then this green circuit board, or black in the GIF here, it's just housing all these various chips that are usually inside of which store your actual data. So specifically, these things here, these DIMMs, they store your data in a volatile way. So it's only working when the power is on. So when your laptop has battery and it's running, or your laptop's plugged in and it's running, which is to say that when you double click on an icon on your screen, when you run some program, if you run something or open some file, those files on your computer are loaded into these little black chips here that you'll see on this green stick of RAM, which is to say that they get loaded into RAM, into the random access memory, and that memory is really quick. It's where those files, it's where those programs run from. So, caveats, other devices have slightly different looking sticks of RAM. This smaller stick here, this little wider one, is actually typically found again in laptops. You can see on the GIF there, or certain desktop models too, but it's the same idea. It's just a slightly different form factor. That means to say that you can actually see it in your computer sometimes exactly how much memory you have, how much RAM you own. Especially if you bought the computer without really knowing this concept before, or given the computer if you didn't think to ask, you can actually have a look in the system settings like this. So in fact, in Windows, perhaps on the so-called Task Manager, if you were to look here at the CPU tab, you might see something a bit like this. And that gives us then a nice little chart there where what your CPU has been doing essentially over the last couple of seconds. And again, the higher the peaks are, the busier it's going to be. So maybe you double click on an icon, maybe you played a video here, maybe you send a really big email, something like this. But I think more interesting than that, perhaps down there, is the actual speed of your CPU. This one in particular was 1.94 gigahertz, and giga or jig, that actually means a billion. So that means almost 2 billion things per second, crazy enough. So that's you at 1.94 billion. It means your computer, essentially the CPU, can do 1.94 billion things per second. Additions, subtractions, multiplications, whatever. Okay, any number of other things. But again, odds are, this is probably marketed, they rounded up, frankly, it's 2 gigahertz, big whip, but it just has this thing called burst technology. We know this as well in EC2s as being of a T family, where it actually means it can go a little bit faster than that, up to a maximum perhaps of 2.81 gigahertz. So that's actually it being overclocked, or using a bit more energy, and frankly, just for some tiny amount of time, therefore generating a bit more heat, because it's actually overclocked. It's not a good thing to do long term, but you can just get that burst of energy when you need to. So you'll see that there's actually only one socket, and which, again, in Windows here means that there's only one CPU for this one. But that CPU itself only happens to have 2 cores, which just means, again, the computer can literally do 2 things at once, because it really is like it has 2 brains inside of that device, of that picture we saw a moment ago. But logically, it thinks it has 4. It seems like it has 4. So this particular PC here, the screenshot with 2 cores, each of which supports a technology known as hyperthreading, which means that each of those cores itself will present itself to the Windows OS as though it's 2. So, which is to say that each core will do 2 things simultaneously, thereby giving me 4 logical processes, or really just the ability to do 4 total things at once, okay? Perhaps even lower detail than is perhaps germane. These kind of things that you do end up paying for in a store when you buy a computer online. This is what distinguishes a good computer from a better computer, or maybe more expensive computer, because it's a rough measure of how fast it is, how quick the CPU is, and how much energy, how many cores does the CPU have, and therefore just how much work can you get done in any given moment with that computer. How quickly can you work more generally, so to speak. So that's a rough snapshot from Windows. Again, for Mac, if you open up the system profile, I think it's called, you'll see a different kind of interface, but same idea, similar information. This is taken from a MacBook Pro. Again, you can see the CPU here is going to be 3.1 gigahertz, so faster. But this one only has one processor, and the total number of which is 2. And so we see no notion here of hyperthreading, which generally Windows is a bit more detailed than at least here. But it does mean that the CPU is still pretty fast. It's apples to apples, 3.1 billion things per second. It actually has 2 cores, so it can do at least 2 things at once. Okay, well, that's my CPU, which, again, we saw the CPU does all the thinking, it does all the work. Then we saw RAM and random access memory. We're going to have a look at now, where all the data, all the programs are stored, and when we're using them, what other things do we need too? Well, what other things might I need for my computer to work aside from my RAM, aside from my CPU, perhaps? What are those programs actually going to be stored? So if I'm thinking about what my computer is made of, if I put things in a box, okay, a hard disk. So all the programs, all the files, all the things I'm trying to load, essentially, when my power is off, when it's not switched on or my battery's dead, perhaps, or my computer's not even plugged in, I definitely need something like, as AJ pointed out, yeah. So odds are, again, if your computer's a bit like mine, that you shouldn't lose all your files, all your programs, just because your battery dies or because you move your computer and therefore unplug it from a wall. It wouldn't be a very useful device without somewhere to store information on. So let's talk about that. Again, so computers nowadays, they have what we call non-volatile memory, which sticks around even when the power is lost. But it uses a different kind of technology for that, different thing to RAM altogether. It tends to use, like AJ says, a disk, like a hard disk perhaps, as is the case here. So there's a device, one that you stick in your PC, on your Mac, or your desktop perhaps, and it stores it stores more information than you would do in RAM. So one stick of RAM, you might have 1 gigabyte or 2 gigabytes or even 16 or 32 gigabytes. But a hard drive, as this thing is called, a hard disk drive, will typically store much, much more, like orders of magnitude more, like 256 gigabytes, 500, 1,000, aka a terabyte or 2 terabytes or more, which, again, orders of magnitude more than your sticks of RAM. And that is, down to the way that it's actually presented. Inside of the device, if you were to peel it off, meanwhile, is something that feels actually still kind of cool and old school. You're going to find that it's made up of one or more metal platters, that literally physically spin around mechanically. And again, on those platters, that's where your data is actually going to be stored. Here, that's your data. So think back to RAM and your memory sticks. There's no moving parts to RAM. Like there's no fan, there's no motor. There's nothing really to spin back and forth there. It's all entirely electronic. It's all electrons at the end of the day. But a hard drive is much more of a mechanical device that actually has one or more of these platters, these disk players, that are spinning and spinning and spinning. And that's what actually allows the computer then to access those different parts from those different parts of those platters, okay? In fact, if you notice these little reading heads, so not unlike an old photograph or an old record player that actually moves back and forth to read the data from the device, but what's really nice about these things is that they are non-volatile. What I mean by that is, it survives the power interruption, okay? Because it uses tiny, tiny, tiny particles. And in fact, if you little specks of magnetic particles, that is, and if you orient them maybe this way or maybe that way, it might represent 1 looking this way, it might represent 0 looking that way, so to speak. So North Pole, South Pole, again, and all that is to say then that there's a very tiny, tiny, tiny particle somewhere here, or billions or more perhaps, depending on the orientation going up or down, representing a 1 or a 0. And again, if you have enough of those particles, you can represent perhaps bytes or megabytes or gigabytes or terabytes or anything as well in between. So now that we have the ability to store data, and either doing this way or that way, even when that power is off, that power that's going to be used to read the data, the actual electricity to maybe write or change the data, it doesn't need to stick around even if just to persist that data. That's the distinction here. So, in fact, I'll just have a better look at what this motor looks like when it's actually running. This is a short video from the Slow-Mo guys, which gives us a sense of where is that thing? Oh, that's really strange. Why does that not work? No worries, I'll just Google it. So I just had a quick video from this from the Slow-Mo guys, just to show you what it looks like, to get a sense of what it looks like when the lid is actually removed, like he's about to do, and then take it from there. So read and write data, the actuator arm, it moves very fast. So that's what you can see here. Trying to find those magnetic particles looking up or down. It just moved 22 times in a second. So the Slow-Mo guys get the name from slowing things down, as you're about to see. Hypnotic. It also, what does it say? It is also well known that all hard drives are waterproof, although I probably wouldn't advise it. It's to be taken as a joke, obviously. Do not put water on anything. I mean, yes, it is resistant to water, but notice that the water probably gets in other places too. Yeah, if you get other parts soggy, it won't work as well.
All right, so actually, if they fall, if you drop them.
Yeah, well, exactly right. So the precision involved in this, if there's another video I had in mind, if fascinating, I know. Let me have just a short clip from a TED Talk. The reason that we have to be a little bit careful when it comes to bumping up your computer is precisely for that reason. If they fall, you might knock those ones and zeros the wrong way. So if you, again, in the depiction here, if you see that these are going to be magnetic particles, which again are ultimately represented as red or blue, up or down. Okay.
So how does it store so much information in such a small space? At the heart of every hard drive is a stack of high-speed spinning disks.
Yep.
With a required purpose. Each disk is focused on microscopic magnetized elements. and your data doesn't live there in a form recognized. Instead, it is recorded as a magnetic.
All right, so obviously, like these are represented now as red and blue, which they represent exactly where those magnetic particles are that then go on to represent your ones and zeros. So if you have a brief pulse of electricity here, which is sent to that read-write head, it actually flips a tiny electromagnetic thing just for a fraction of a second like this, and that magnet goes on and creates a field which changes the polarity of a tiny portion of the metal particles, which coats that platter. And that pattern is again a series of those tiny charged up areas, which that disk then represents as a bit of data, and that bit of data in the binary system, a binary digit is then used by computers upstream. So if the current is going to be set one way through the read-write head, the area is going to be polarized in one direction. If the current is set in the other direction, the polarization is reversed. So that's how we then get our data off a disk here. We just reverse the process, So again, the particles of the disk that get the current in the read-write set, if you're moving this way, if you want to change that data, you just do it the other way, You put them together millions and billions of those magnetized particles, and now you've got yourself together a file or an image, Now, the pieces themselves on a single file, they may be scattered all over the place on a single hard drive, like you see here, all over the place, and it's kind of like a mess of papers, on your desk. So there's often another file that actually keeps track of where everything is, and that's what you call a file allocation table. It then remembers where it actually stores that information on disk, so that anytime that you have a physical device like this, that Chantal pointed out is likely to be spinning all day, or maybe months on, weeks on, years on end, and if perhaps you use your computer a lot, then for a long dedicated point of time, something could go wrong. Maybe you accidentally bump the desk or the laptop, you fall or something. The result of which, that if just wear and tear alone, is that the reading of this head might actually strike the platter of your metal disk, and it might make a dent in it somehow. It might make some kind of scratch, perhaps, which actually will corrupt the data. Not perhaps just some of the data. Maybe it actually stops the whole device from working too if you're unlucky, or if the read head no longer functions correctly. Again, anything that's physical in this world is going to have this finite ceiling. It's actually not going to spin that fast at the end of the day because it's physical, and technically it might spin up to 1,000 gigabytes per second in an inch squared. It might spin a couple of thousand times per so, but that's still much lower than the speed at which these electrons here, these red and blue electrons, might be able to flip. So something like you might expect to see in RAM, perhaps. Okay. Now, unfortunately for us, though, there are other technologies by which that they don't have moving parts. There you go. I'll send that video if you want to go watch it again. Something which is not quite as fast as RAM, but doesn't have any moving parts too, which is that of a so-called flash memory or solid state drive. And this is now the approach, the solution we came up with. So an SSD, for instance, here it is actually smaller. Whereas typically hard drives have moving parts, because it's got to move. Very often these are like 3.5 inches, although 2.5 inches do exist too in diameter. Well, a solid state drive tends to be a lot smaller in width, so it actually fits inside of your computer in what's known as a SATA connector, in the same slots that older, more mechanical drives might fit in, but it actually doesn't have any moving parts. So in fact, if you open this up and you look inside, you might see something quite reminiscent again of how RAM looks. But the technology inside of this device is such that the data will persist. Even when your battery dies, even if you unplug your computer or your laptop. But the upside now of it being a solid state drive, SSD, being entirely electronic, no moving parts, is that it's much faster. It means that your programs will load faster when you double click them. Your files will open faster when you double click them. Anything that you do or save to your hard drive or your solid state drive, in this case, will actually get saved much faster, which is, you might see like a little hourglass or a spinning beach ball far less frequently, okay? Your computer is certainly going to behave and certainly feel faster, but the catch is that solid state drives, theoretically, they won't necessarily last quite as long, depending on the quality of the brand and maybe the technology being used, by where you have a finite amount of writes. There is an end of life to everything, and you can read from them nearly as much as you want from this, but over time they too will degrade in terms of how many times you can keep writing to them. Again, for many people this will be a non-issue, but I guess to mitigate against this, the industry has introduced what we call hybrid drives to fight back against our MTBF, our mean time between failures. Hard drives that might be the same size as kind of this, that is 3.5 inches, or the spinning mechanical drives from a moment ago, but they might have both a solid state drive and some mechanical hard drive, so that you might have a few megabytes or gigabytes of solid state memory, and you might have a few gigabytes or terabytes of traditional hard disk drive. And so that hybrid device is actually going to have the best of both worlds. So it will move your data around in a clever way so that it tries to keep as much of the data that you want to have, what to use at any given moment, on the solid state part of the information. And so, that's a bit that's readily accessible for you. And the data that you might not need, the kind of archiving data, that right there and then stays on the, stays in a slower, much more mechanical form, nonetheless, giving you much more storage. Oh, just remember, I forgot to send you the notes, so I'm going to send that over now. Sorry, I forgot to send you the notes, which I'm going to do right now. Where on earth are they? There you go. Okay. And perfect, cool. So we talked about this. Well, hard disk drive then, usually just free storage. Basically, how much room do we have literally to store files on our machine? How much memory do you then have? Maybe you don't know or don't care. But again, if you do look at your system information or look at the computer you might have bought on the internet, you very much do find that in terms of quoting terms of RAM, you might have a few gigabytes of RAM. It usually scales on the of like as high as 32 or 64 RAM, which is quite a bit more than what we just talked about. But generally, for really high-end computers or high machines, computers today, especially those that do process a lot of graphics or like gaming machines, so specifically computers that are specifically dedicated, you employ more RAM. I can't zoom any further, but again, that range will be nowadays between 4 and 16. Again, but when we're talking about hard drive space, I've got a few, as you can see. That number tends to be a lot bigger, a lot higher. It's not showing up for some reason. Oh well, it is at the bottom. It's just not very presentable. So again, the typical hard drive or the hard disk drive nowadays might be as low as 100 gigabytes, I think, the very, very low end of stuff. Again, versus a hard drive. I'm not going to go into this in too much detail about those two things, other than to say that there are two different ways of storing that data long term. Okay, the high end is probably up, on the magnitude of, I think, 2 terabytes. I've got is one of them. So let's have a look at drives or disk manager, F disk. Well, I'm not going to format just because I'm scared to go through that process, but basically just quite a bit of memory, okay? As much as like 4 terabytes, which is quite a lot of storage information, and that's enough to store, several high-D movies and stuff. But again, there's much, much more than to just RAM and hard disk space too. There's actually a kind of hierarchy of information that sits on your machine too. So again, most of these numbers, although they're not usually quite in the specs of a device as much, we have RAM, of course, so random access memory. Then followed 2 is a series of these so-called caches or caches, again, each of which gets successively smaller and smaller and smaller. So they're going to be quite a bit smaller than, say, like the 4 gigabytes of RAM that your device might have. But they're a bit faster, And the reason that they get faster is that these caches get smaller and smaller and smaller and smaller, closer and closer to the computer's processor, which, is really the only part of the device that's able to manipulate that information. It's the only part that can process that information. So the memory that we're going to be feeding to that processor needs to get faster and faster, such as that it continues to swap things in and out. So we can have the RAM, and maybe a layer 3 cache and a layer 2 cache and a level 1 cache, and finally the CPU memory, which is the processor memory itself, plus some bits of memory too called registers, which used to be the final sort of, the final pass of information from RAM to the so-called, of memory to the so-called CPU. But again, every single file on your machine typically somewhere lives permanently on a disk. Again, there are two sides of the story, two kinds of disk drives. We have the solid state drives, which we've seen, and the hard disk drives too. And we should treat them effectively as identical for the purposes of, just today. Solid state drives tend to behave a bit differently than hard disk drives. They tend to be a bit more secure when we think about the vulnerabilities in a second, because we're going to see in a bit why. But in general, when we think about hard disks or solid state drives, just storage space, let's say, for today at least, we're going to be focusing mainly on this one. They're just, again, very prevailing still. Everyone's got them. Solid state drives are coming into their own, and they're becoming more and more frequent. They're getting cheaper too. But hard disk drives still are, much more prevailing still with that device usually, at least today. Not forever though. They are still just space, ultimately just storage space, though we can't do anything with that data stored on disk. We first usually have to move it into RAM and then go up or go down on that chain of RAM and then have the different caches to the CPU in order to then actually manipulate the data. Once we're done manipulating the data, maybe we're turning our computer on and off in the evening, all the data that's in RAM actually will be stored back into the hard disk space so that we're able to access it some other time. Volatility. One other thing to keep in mind too is that memory is really just an array, which, we talked about arrays last week, where each cell of that array is basically 1 byte wide. And recall that 1 byte is 8 bits, and we may have anywhere between 512 megabytes of memory. So 512 million of those little ones and zeros or bite-sized cells, maybe size 4 or 8 or 16 or 32 gigabytes and so on. We have a few different items in the array. But an array is really it just means that we can then jump to different addresses. It has the same properties of any other random access array that we've already discussed before. Different types of data, though, takes up different amounts of memory in our systems. And if you think back to like a very, very low-level programming language like C or Fortran, perhaps, which is really just, from like an example, different programming languages may store different types of data in different amounts of space. But if you look at the most base level of data and think about the individual pieces of data which we can break into, we may be able to store something like an integer, perhaps, which, for example, here would be about 4 bytes, which means that we can have exactly 32 bits worth of space to store an integer. Characters will take up 1 byte. So we already have 8 bits worth of memory just to store a single integer character. Capital or lowercase letters, digits, anything on your keyboard, essentially. Not a huge variety of characters there. Floats. Well, if you recall that they are real numbers, numbers that have a decimal point in them. Doubles as well. They're just double precision floating points, and they take up 4 or 8 bytes. So basically, the idea here is that different types of memory will take up different amount of space. Then eventually we will be able to construct these things into pixels, into images, into films, into objects more generally, each of which will take different amounts of space and memory if we're manipulating and working that data. So again, just to rewind, if you think about memory then as this big contiguous, this array of individual bite-sized cells, and because it's an array, it means then that we have random accessibility, which is we say, I want to go to memory X and I want to see what's there. Okay, I want to go to that address over there and I want to change what's in there. We have the ability to do that with this. We don't have to then iterate through every single step by step in order to get and make those changes happen. Because otherwise, if we did, it would actually be a lot slower having to perform that. Okay, we might term linear search if you try to iterate through memory. If you think back to those algorithms we looked at in order to find the 1 byte we're looking at for, so it's helpful then to just jump to a particular byte. That means then that every location in memory will carry with it a particular address, and then that gives us then a way for us to refer to an individual byte in order to randomly access that. We can't just look at this grid of cells and say, I want to go to this one and sort of imagine this particular spot. What we need to say is, I want to go to exactly this memory address. I want to go to that particular parking bay. And so the fact that memory cells have an address is, this comes into play when you think about this idea of a 32-bit system or a 64-bit system, and this again might be a term that you've heard before. It refers again to the ability to process one of those addresses. So for example, a 32-bit computer, a 32-bit system, it can process memory addresses up to 32 bits in length, which means then that it can understand memory addresses, 0 through memory addresses up to 4 billion, 4.3 billion, give or take, but it doesn't really understand memory past that. Now, interestingly, that doesn't mean that a 32-bit is limited just to 4 gigabytes of RAM, 4.3 billion. There are some clever tricks. We talked about hyperthreading amongst them, where you can pull something called virtual memory, I'm not going to go into more detail right now, just to refer to it as virtual memory right now, okay, which just allows you to use more than 4 gigabytes of RAM or 32-bit system by doing sort of pretending that there are things that live somewhere that they don't. But when you think about a 64-bit system, well, that means we have many, many more cells that we can refer to without running into sort of an artificial limit as to how high we can count. Now, granted, yeah, there are no memory banks out there that have all the memory addresses, again, from 0 to 64 bits worth of memory, I don't know, somewhere in the quintillion or higher. But it's a very, very, very large number that we don't yet have the storage capacity to store that much data on machines anyway, due to the power of whatever. But theoretically, it's possible then that with a 64-bit system, we could have very, very large amounts of RAM. And again, the more RAM we have, the more random access memory, generally the quicker that computer is going to operate because there's more space for it to store information. It doesn't have to keep sending things back to the hard drive when the RAM is full because there's so much information being processed at once. More of that is available at hand. It's quicker then, more accessible bits to memory. So just remember that with each bit, like a bit can either take on one of two states, 0 being off, or you can think about this in terms of power, electricity, which is how RAM actually works, right? Being unpowered or powered. So that means we have 2 to the 32 power, possible memory addresses. So 2 to the power 32 gives us 4. This number comes up all the time. 2 to the power 32, 4.294 billion or so. Okay, let's say 4.3 billion memory addresses. Now, sometimes then, the case that programmers and subsequently people who might need to read code actually find a way or refer them to find specific memory addresses. But again, a memory address actually looks like this. That's what a memory address really looks like. These are the ones and zeros in that address. That's exactly how we would again refer to an address in memory. It's kind of cumbersome. No one wants to talk to another person. No programmer wants to hear, wouldn't talk to someone else just saying the code 001011000 and so on. It just doesn't make any sense. That's not how you and I would talk because it would just take forever, in the name of the memory before you even get to the point of what it's in the memory. So rather than us using binary notation to refer to a memory address, computer scientists will often use something called hexadecimal instead. Hexadecimal is 16, so hexadecimal 6 and 10. And so this is the case of the base 16 of a number system. It's just a different number system that has the decimal system. So we think about base 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we go back to our 10 digits again, decimal. So that's the one we've used forever, just to understand place values and the numbers and so on. But what's convenient about hexadecimal, again, base 16 now, versus a binary, because that's base 2, 1 or 0, is that in hexadecimal, 4 bits can be represented as using what's often called a hex digit. So for every group of 4 binary digits that we have, we can represent that much more succinctly, let's say, just by using one hexadecimal digit. And again, because there are 4 bits, that means we have 2 to the 4th or 16 combinations, so we can actually account for every single possible combination, on or off combinations of all the 4 bits in that cluster being a single hex digit. Or, so we might actually refer to this particular memory address as looking like that. And so there are actually some character letters in here too. You can see D, E, and so on. And that's just to represent a single digit in hexadecimal. So we need to be able to count higher than 10 using just 2 digits because we're now combined to this in hexadecimal. So in order to represent the number 10, we need a 1 or a 0, 1 being in the tens place, a 0 being in the ones place. But in hexadecimal, we need 16 possible digits just to represent all the possible 16 values without, at any given point, in any place value. So if you can wrap your head around this, here's an example of what a lower-level programmer would see. This is something, so this is using a tool, GDP. This is a debugging tool, which again is going to be used to debug or maybe just root out and find problems in some low-level code like assembly language and the like. And what we're seeing here is a bunch of memory addresses. So I've gone ahead and highlighted them here yellow, so we don't have to worry so much about the context around this. I don't even know myself what they actually refer to. But basically, the things here on the left, so EAX, ECX, and so forth, these are the registers. These are the things that are really close to memory, and again, they are storing the memory addresses of something else. And so all the things on the left here, these are just the memory addresses. And the things on the right then, these are the so-called translations of those memory addresses. And in the case of actual decimal numbers, that might make more sense to us, having used the base 10 system, that we know better for some time now. So again, if we can then take that information, we can map that into all the possible values in hexadecimal to the binary equivalents, and as well as the decimal numbers that we're familiar with. So again, here we have all the possible combinations of all the 4 bits or zeros and ones showing up and showing you what they translate to in decimal. Recording that every set of 4 bits, here we see, the one on the right is the ones place, then the second from the right is the twos place, and we have the fours place, and then the eights place, because again, our base is 2. Every place value is a power of 2 as opposed to a power of 10, like we would have in decimal. And so then the hexadecimal equivalent, so again, for every single one of those combinations, we would have a distinct way of representing it using a single hex digit. And so sometimes you'll see the hex digits 0 all the way through to 10, through to 15, given through like presented against like capital letters too. But sometimes you'll see them in lowercase, uppercase letters too. It doesn't really matter too. So this 0x that happens to the left of it here, I should mention that as well. So 0x just means absolutely nothing. Okay, it's just purely a note for us as humans here, just to, again, when we're seeing something like this, that we then know to interpret this as hexadecimal numbers as opposed to decimal numbers, for example. Because again, we can see a very valid hexadecimal string, that is going to say, I'm going to use 0x, just for here a second, 0x50 or something. And again, if I might see this, we might have read this, if we didn't have the 0x in front of it, we might actually see that as like 123, which actually would not be accurate because again, 0x is 123 is actually another number entirely in decimal location. So this 0x here is just it's just a guide again for humans just to say, okay, what I'm about to see, what's about to follow then is itself a hexadecimal number. Okay, so just to see, again, a quick exercise where we're going to translate a bit of binary into hexadecimal and then subsequently turn that into decimal too. And so again, we have 1, 2, 3, 4, 5, 6, 7, 8 bits, each of these bits, again, is going to be a 1 or a 0. Again, our goal now is just to translate this into ultimately decimal, so that's 0 all the way to 9. But let's start just by translating into hexadecimal first. So the first thing is we're actually going to count from right to left, and we'd like then to split these things into groups of 4. So it so happens to be that we have 8 bits here, and so this splits pretty nicely, cleanly into 2 groups of 4. But if again, we had maybe like 7 bits. Like if it wasn't the case here, well, we could start by halving 1, 0, 1, 0, and then we had whatever we had left over. Essentially, we would actually pad a little extra couple of zeros at the front there, so we would always have a cluster of 4 bits at the time to work with. So each of these maps directly to a single hexadecimal digit. And sometimes you might be able to do this quickly in your head. I don't know why you would, but you could jump up, you look at the table here just to see this particular pattern. So I want to plug this particular hexadecimal digit. And if you do this here, so if you do the one on the left there, so 0, 0, 1, 0, again, this is a binary again, is 0 in the ones place, a 1 in the twos place, and then nothing else, and then nothing else. Well, that means that we have 1 times 2. And so this will actually give us a 2, because that's in the ones place, that's in the twos, in the 4, and the 8, and the 16, and so forth, okay? But 2 times 1 is 2, so that's 2. However, if we look at this one, well, 1, 0, 1, 0, that would actually give us a 1 in the 8th place, because that's 4, and that's 2, and that's 1. A 0 in the 4th space, 1 in the 2's place, 0 in the 1's place. Again, 8 plus 2, that gives us 10. So, but again, this in hexadecimal, if we represented this better, that would actually give us an A, because we just need to confine this idea of 10 to a single place value. So we can't have 2 digits representing it by using hexadecimal notation. Exactly, in the case of 10. And so this binary value, again, so 0, 0, 1, 0, sorry, this one, again, the human convention is just to pretend that there's a 0x in front of it, just to kind of signal what's about to follow. And this, again, is a hexadecimal number, so 0x2a. Well, how do we translate that into decimal? Something that you and I can think of. Well, it might be more helpful just to think about how we translate or understand this number, 123, 123. Now, when you and I see this number, 123 just written out, well, we're actually doing something like this in our head when we're saying there's a 1 in the 100th place, there's a 2 in the 10th place, there's a, there's a 3 over there in the 1's place. And we've just over time internalized that we've been able to very quickly understand the number that we're talking about here is 123. Well, another way to think about this, not 123, is as these labels instead, okay? So 100th place, the 10th place, and our 1's place. So that might be to say then we have 10 squared, or 10 to the second power's place, 10 to the first power's place, and then 10 to the 0 power's place. So any number to the 0 power is always 1. And so, this is really just the 1's place, the 10's place, and the 100's place. So with hexadecimal too, well, we don't have 10 anymore because of the base exponent instead. Instead, we have 16 as the base of the exponent, but the rules are still the same. So we have 16 to the 0's place, which is 1. We have 16 to the first power, or the 16th place, and we have 16 squared, which is 256. So in our example here, we didn't go that high. We had 0x2a. We only had 2 digits, mind you, which means that we only really needed 2 of those place values, but 16 to the 0 power and then 16 to the 1 power. Now we can translate that in the same way we did before. We would intuitively do when we're kind of counting a decimal or reading a decimal number to give us this. So this is to say 0 times 16 squared plus 2 times 16 to the first power plus a times 1, or 16 to the 0 power. So 2 times 16 is 32, and a, which again, hexadecimal is a way of representing 10. So 10 times 1 is 10, and what we're really saying is now we have 32 plus 10. So just to translate then this hexadecimal number, 0 times 2a into decimal, we would end up with 42 because 42 is 32 plus 10. So the meaning of life. Hopefully, that gives you a better understanding as to what these cryptic numbers, what these strings actually look like. And, if you maybe seen them before, that might mean what you now know. But again, if you're working with programmers or if you ever need to analyze source code or just see references like this, hopefully we don't need to, but it will give you a better understanding of what they actually mean, what they're likely to refer to on the system and how that might affect things. But hopefully, unfortunately, we work in a high level from this. Just to think a little bit more about the function though, like how memory actually works. Now that we know how to access individual parts to it, using the address, again, well, the one exception to this is the hard disk space. So again, the permanent storage space in the device. So memory in your computer is volatile, which means that there are 2 different things. One is that memory is constantly changing. So things are going to be cycling in and cycling out of it. It's very dynamic in terms of the values that are going to be stored in there. Again, because RAM is sort of holding ground for everything that is eventually going to be fed into the processor. So things are going to be swapped in and out constantly and pretty frequently. But the other really key detail about being volatile is that it draws power. That, if it's left unpowered, if there's no electricity literally flowing through to the RAM at any given point in time, then that's a problem. That memory will not work. It will not be powered. And so just after some amount of time, I think a pretty small amount of time, like 30 seconds or maybe like a minute perhaps, without power, without electrical charge, which is again used to maintain each of those individual cells of memory. Remember, so a little bit of electricity being 1, or the absence of power being a 0, that's how the computer is able to store this idea of 1s and 0s on the physical manifestation thereof. Because without the power, that electrical charge eventually dissipates, it goes away, it doesn't stay. So the state is eventually lost in such a way that if it's unpowered for, let's say, a minute or so, I don't know, but all the data in that RAM is essentially turned back into 0s. It has become completely unpowered and unusable. Now, obviously, that would be really bad if your entire system relied on this technology alone, but it's only RAM. It's only the caches from RAM that, going this point forward, actually rely on this volatile memory. Because we said processing itself happened to the processor. And that maybe makes a bit more sense because, again, remember that we have 32-bit processors that can understand 32-bit addresses. That also means that it has 32 bits of space, which to do anything with. So it can only work with 4 bytes or 32 bits of information at one time. Again, if you have computers with multiple cores, if you have a 2, 4, 18, I don't remember how many cores I have. Quite a good one. 14 cores. Again, multi-core processors. You might have a few of those processors that actually can do 14 things at once. But anyway, you're talking about a very small amount of information, maybe like a couple of bytes here or there. It's not that much. When you consider like a basic document, maybe like PowerPoint, for example, or Microsoft Word, that will have enough metadata for, let's say, like 15,000 bytes before you can even type a single character into this. So there's a lot of metadata that goes into this, and a lot of empty files too. Because the process, it can only hold 32 bits worth of information at any point in time, any given processor, because we need to move data frequently to this. And that's what the caches are for. That's why each of those layer 3, layer 2, level 1 caches needs to be faster and smaller to be able to get more information to it pretty quickly. Because even though the processor can only process 4 bytes or 32 bits worth of information at any given time, it can do 2 to the 3 billion operations per second, which is, again, what those gigahertz were for. And in terms of when we quote a processing speed, sometimes it says, so 4.5 gigahertz and so forth, that means this computer can do 4 billion things per second. So again, 32 bits, not a lot of information at any given point in time, but there's a lot of those instants within a second. Okay, it can do 5 billion things per second, and each of those things operating in exactly like 4 bytes at a time, or 32 bits at a time, on a 32-bit processor, which this is, as opposed to a 64-bit processor, which can process them a little bit more data, let's say. Okay, just take a look now. If we wrap your head around what we determine on your computer as the motherboard, again, sort of the an older image perhaps, but it's just one that had everything on screen. So this does highlight some of the different places where things live in your physical device. So, for instance, here you might find slots for your RAM. Essentially, those are those sticks that get plugged in. So RAM stickers, again, we saw like green chip. It looks similar to the motherboard itself, red in this case, but generally green. And they do have some gold connector pins at the bottom of them, and they plug into the motherboard. Information that can be stored in that just to flow through to and fro, and then when it's needed by the processor and so on. That's where these things will actually go. This particular motherboard. It's about 100 years old, so I don't think most of us have things like floppy disks now, but this one still does, so bear with it, okay? Here, though, is where the CPU would live. So that's where the actual processor would go. And again, that processor can only, it can hold about 32 bits or 64 bits worth of information at a given point in time. On top of that CPU, although not depicted here, typically on top of the CPU, there's a giant fan, literally like mounted or screwed right above this. And again, that's because the computer's doing 5 billion things per second. So it's a lot, and that gets quite hot. So to prevent the CPU meltdown or a cold meltdown, you would make sure that you had a constant supply of air flowing across the top there of the device, as well as a heatsink as well, just to pull the heat away from the CPU, such as that it doesn't overheat, which would create a big problem if it might eventually result in the computer melting if you're leaving it to overheat for a long time. Okay, this is where your integrated, so that's where your graphics processor goes. Graphics processors are really just CPUs, okay, but they're specialized to do certain operations that make interpreting graphics on your monitor such in a way that's easier. The maths for them is probably a bit more complicated, so modern devices may have both a CPU and a GPU, a graphical processing units, as opposed to just relying on them being integrated, trying to do both in one, trying to do those different tasks together. And so that similarly would also have a heatsink and a fan with it as well. On top of that too, it's pretty small, but there are things there like your SATA connectors. So SATA connectors are what you might use to connect to your hard drives, to your machine. So again, that's how you then extend the storage capacity of your device. But all these things that live in your computer, all of these things are sort of shrunk down kind of a form that live in your laptop and live in your phone. The basic idea still exists in just smaller and smaller scales, with the parts also being similarly scaled down. Okay, so again, the CPU memory, what actually lives in the CPU as well as the registers too, really those fast things are the CPU memory. That is the fastest memory on your machine, but there's also the least of it. And that is for the reason that it's very, 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 very expensive. It's the most expensive thing in your computer is the CPU. Basically, that's the price you pay when you buy the computer for how fast that processor is and the materials that are used to allow electricity to conduct through it very quickly at the time of the cost end of your device. It's the most expensive because there's less of it. Again, but it's also the most important part of your machine. The caches, though, layer 1, layer 2, layer 3, are each successfully slower, going upwards because but they're also successfully cheaper. So your layer 1 cache is going to be a little bit slower than your layer 2 cache, other way around, than your CPU, because there's generally going to be a little bit more of it, and your layer 1 cache will be a bit larger than the CPU space, and you might have a little bit cheaper too. Again, and I'm just referring to the materials that are used to make the memory operational, but RAM is slower, RAM is cheaper. But RAM is, it used to be the most expensive or considered the biggest driving cost. Again, if you had more RAM in your machine, that made it more powerful. That was the cost driver, but it's becoming less and less now the case. Still more expensive than the hard disk space, which is essentially just, it's free at this point almost. It really just shows at scale how much stuff we can literally fit into the container for the hard disk itself, which is again just pure storage. Better known as Moore's law, if you follow that pattern. But RAM itself, slower memory than any of those caches, but you're able to have more of it because it is less expensive. Okay, so that's memory. In terms of hard disk space, it doesn't really work in the same way as RAM and the other volatile memories work as well. And the hard disk space is non-volatile. Information on the hard disk is not changed that often. Only when we're certain with it, when we're done working with the RAM, when we save a file, are we certain we want to change those bits. So the data inside of a hard disk space is persistent, and that's because it doesn't rely on electricity to store the data or to store state. Rather, again, we're talking specifically now about hard disk drives or HDDs or solid state drives. They work a bit differently because instead they use microchips, they do different things. But when we're talking about hard disk drives, traditional hard disk drives, spinning patterns and the like, each cell of the hard disk drive is instead controlled by magnets. Okay, so that data stored magnetically. If there is, we'll just say for the purpose of today, if that magnetism is in the down position, so south, for example, if it's oriented south, that'll be a 0. That's one way of representing 0. So any magnet that's in the up position is 1. And so we can have these flip states of the polarity of pointing up or north, the polarity of pointing down or south to represent the 0, as opposed to powered versus unpowered to represent a 1 or a 0, respectively in RAM or the volatile memory solution. Because again, those magnets, though, magnets don't need power. They're not waterproof, but again, they need power to work in the long term, which means that when the computer turns off and they become unpowered, your data lives on. That's what makes them non-volatile. And that's a really good thing, I suppose, because now every time that you go to bed or turn the computer off for the night, otherwise you would literally lose all the files that you ever saved on it. That would be terrible. It would not be. We couldn't do anything with this. We would lose a lot of the utility that we rely on computers for. So the way that hard disk drives work is specifically designed in such a way that memory can persist after the computer's turned off, and that's why. So again, in contrast, memory is not processed directly in the hard disk. We have to then move it to the processor eventually. We know this. It goes to the CPU. And so if our system detects then that we need a chunk of memory from the hard disk drive, that's going to be first moved from the hard disk drive into RAM using something known as a bus. And maybe that's a good point just to get on the bus and think about the coffee break there, AJ. You're right. Yeah, I'm sorry, just looked at the time, got distracted. Let's think about this. Come back in 10 minutes if you don't mind. We'll talk about the SATA connectors in the bus, getting memory from your hard disk drives into the bus and down to the CPU, if you're willing to do that. Yes, so it is I. Who won? Wilson! Wilson is the winner. Yeah, did you know? How did you get that? Congratulations, Wilson. How do I stop this? I'll just, I'll keep it running forever. As a treat, I'll show you what was disrupting me today, Wilson. This is my view from the window a few moments ago, if I find the video. I'm not kidding. I have some trees outside of my house, and they're cutting it. I'm so distracted at the moment because they're literally cutting trees. I just took this video right now, okay, so for you to see. There's a guy with a chainsaw chopping down trees, and his friend is also chopping down trees to the side. Yeah, I know. That's a little bit of a gift for you. So forgive me if I'm distracted. It is quite an exciting thing. So, anyway. Okay, well, why don't we circle back to this? Just for those, if you join a bit later to what Zoom allows, there is a handout I did have, and I'm using just to send over. Let me just resend that in chat for you. So we get going with the idea of a bus. And now this is something that I've noticed does appear in the terminology of the wording of the event bus, that is event bridge. This idea of moving event data from in your AWS environment is really related to the way that memory works too. Much like how, say, a bus is used to move people from one place to another, like in large quantities, a bus and data is used to move a large amount of data in one part of your machine to another part, again, in large quantities. And in fact, have you ever seen these things called SATA connections, again, from a hard drive to your RAM, using SATA connectors we saw a moment ago on that picture, on that diagram? Usually they're like these long, thin strips that connect them two together. Well, that strip actually forms part of the bus. That's the thing that's used to transfer data from one hard drive to the RAM in big amounts. So in general, when we're working on a program, that data for that program, including the code that's actually running itself, is going to be moved from the hard disk to the RAM. And it stays in RAM, assuming that there's no space constraints, and that forces it to have, which sometimes can happen if you're running a lot of programs at once. You probably notice your computer slows down quite a lot. And that's because your computer is going to have to keep, attending to different things, keep swapping things in and out of the RAM in order to process multiple things at once. And that's why, folks, you don't want to leave hundreds and thousands of tabs open. My mom does this all the time. I tell her not to because she complains. Why is it slow? I wonder why. And she has like 30 or 40 different apps open on her phone, or different programs at the same time running on your computer, which, again, if you can avoid this, because it's going to slow down, it's going to require things to be swapped in and out of RAM, such as that it can actually move to a processor quite a lot. That's really going to slow down things quite some time. So while the program is running and while it's being used by the computer, everything will stay in RAM. All the data is going to be manipulated in RAM. And then ultimately, when we close the program, when we leave the whatever, we otherwise indicate that we haven't used it for some time, it's gone into hibernation. The computer realizes, oh, it needs space again for something else. All those bits, all those bytes that were manipulated into the RAM, will be sort of picked up and then moved back by the bus into the hard disk space, where they'll be resaved with a new state, such as that any changes that you make in the program will ultimately be saved back to the hard disk. But only when the program is completely done being used by the computer, realizing now it can free up some of that space, some of that information, and save that instead for long-term storage rather. Hard drives, though, they are not unbreakable. Okay, so they have a lot of different moving pieces we've discussed already. A typical hard drive consists of these metal platters, some thin metal circles spinning around quite a lot on a central axis very quickly, about 5,000 revolutions per minute or so. So very, very quickly, with magnetic read-write arms that extend over the diameter of the disk, basically. And each of those little rings, like a tree, it gets formed as you do this. And it's the read-write arm that actually moves in and out of it and accesses different sectors of the disk. And those different sectors are the things that get zeroed in ones over time. So it's possible for hard drives too, mechanical things to fail. There's a bunch of ways that can happen. If the read-write arm jams, because it's sort of just on the same track as it moves in and out of, if it jams without collapsing, your hard drive will stop working essentially, but because you can't read or write information anymore using that ARM. But it's also possible for the hard disk ARM itself to break or to fall because that ARM spins just above those disks, and if it crashes into it, you'll hear that crack sound. It's a unique or very interesting sound to hear. And suffice it to say that your hard drive at that point is destroyed. Like if you scratch the surface because that collapse of the ARM will break everything, it'll crash everything. I think they do something similar to this in Breaking Bad. With enough magnetism, those things are spinning very, very quickly, and so they're going to shred themselves from the inside essentially. And that point, you're then no longer able to read that data off of that drive anymore. Magnets. Okay, so it's just that arm again. That if it gets stuck, but if it's moving in and out and it doesn't fall down, you may well still be able to recover data from that hard drive, and we'll talk about that shortly. Because a hard drive failure doesn't mean that the data is unrecoverable if the hard drive literally hasn't suffered this catastrophic shredding sort of thing that happens. That's going to render it unusable or unreadable. But if it's just the arm itself which is stuck, it's still usable. It just needs repairing. So what happens though if we delete something on your machine? It turns out then that overwriting hard disk space is actually a very, very, very time-consuming and what we might consider computationally expensive operation of the machine. You can think about this like it has to pull all of the data from the hard drive into the RAM, change all those bytes to delete what was there before, and then put all of that data back in. So for a computer with very, very large files, so if you want to delete a video, if you want to delete a movie perhaps, that might be several gigabytes, so several billion bytes worth of data that we would have to delete. That computer, it doesn't want to incur that kind of a cost. So it'll be cheeky. And what it'll do is work around it. So deleting a file actually, if it had to do it that way, it would be very, very, very slow. It would compromise any other program that you had running on your machine then, because it's so time consuming. So that's not how computers actually delete information. Rather, I think we've said before is they just forget where they actually live, where they are. And so as it turns out, there's something in your system called a page file. And a page file that lives on your machine, which is basically the home address of the very first bytes of every single file that you have on your machine. And so when you delete a file on your computer, typically, it just forgets where it lives. That byte is made up if it's still in there. The ones and zeros that comprise your file don't themselves go anywhere. They might eventually again be overwritten, or they might be then occupied by some other file that happens to be stored in that same spot because the computer now thinks that it's open because it just forgot what was there. But even then, this only happens when you empty your recycling bin or your trash can in Mac. And so that means if you put something into your recycle bin, that's not actually deleting it in any meaningful way. It just hides the icon essentially. You can't really click on the icon anymore, but you haven't really deleted that file. And I want it gone, okay? Because we know somehow that we can actually restore things from the recycle bin. So even though, there are sort of two levels to this. Even if you empty the recycle bin or you empty the trash can on macOS, you're still not actually deleting anything in the sense that you might be thinking it does when you delete things. Instead, like I said, your computer just forgets what was there before. But those bits and those bytes that comprise those files that you might have deleted are still there. They're just creating a couple of really interesting security implications for us. So now if we agree, if that files don't actually get deleted, if they're not zeroed, they're not really deleted for good, it means then that we can still actually recover information from them if we really want to, under scrutiny. How do we do this? Well, there's definitely some tools out there that can be used to do this for sure. And this again requires the hard drives were not physically destroyed. They're not destroyed in some kind of collapse of the read or write arm, or they're not broken in two. But if we can literally just connect the hard drive to something and have a specialized tool that then reads all over those individual sectors of the disk, and again, this is a very, very slow operation for sure. It will take that, hours or days to read over all the individual sectors of the disk and say, well, that's a 0, and that's a 1, and that's a 0, and that's a 1, and then we end up with this huge file that is all these 1s and 0s that what originally was that state of that hard drive, of that file. And we refer to this file that gets created, this clone of the hard drive, essentially, as what's known as a forensic image. And it really is just a huge file that is a complete replication of the bit-by-bit content, as well as any of the metadata that might have been associated with that too. And the point being that we can then create this clone and we can read on a different machine, so that even though the hard drive that this was plugged into, maybe the computer got destroyed, but we can now make a copy of that, and then we can read it on a different machine instead. So how do we go from, how do we pick out where those files were again? Again, because to go to Lance again, computers only understand 1s and 0s, and at the end of the day, all that stuff that's stored in your machine, in your hard drive, all those files, anything that was stored in RAM, where it was powered on, is still 1s and 0s. Like, they don't have icons like we see on our desktop, but they don't mean anything intuitively. So how do we figure out where those files are? Well, it turns out then that they have most of which, they have something known as a signature. Files will have a magic number associated with them, and a magic number signature is just a way to refer to the first few bytes of a file, where many file types, for example, PDFs, most image files, most music files, MP3s, MP4s, and so on, they all happen to start in a particular way. Now, this is, you and I will never ever see this when we open any of those files. It's all invisible to us, of course, but transparently, if you look at the metadata of any file you have in your machine, it turns out usually there's a sequence of characters or bytes that then represent a signature, in effect, a way of saying, the file that I'm about to open is a PDF. And then you can generally rely on the fact that because of these first 4 bytes of whatever, of these values, now, again, it's going to be 4 to 8 bytes. It just means that there are 2 to the power of 32 or 256-ish possibilities for what those first bits are. A lot of different combinations, okay? So if we see that a magic number appears in the forensic image, on the hard drive, the clone, shall we say, odds are then pretty good that if we start to see that pattern, that signature image, we know then that pattern refers to a file of that type. That's what we would have found in the beginning of a file of exactly that type. And then from that point onwards, we can then start to interpret that in a way and then maybe be able to reconstruct it from something else. So I've got a list here perhaps of some of the most kind of common file types you can find nowadays. So PDFs, for example, in our case, PDFs have this particular metadata. And again, we never see this, right? The characters percentage PDF, beginning of them. And it turns out then that this translates to this sequence of bits of binary digits using the ASCII table that we've talked about before. We don't have to go into detail once more, but this then translates into those hexadecimal values. And so generally, if we happen to encounter exactly this pattern of 32 bits, which again, we would only expect them to find at the beginning of a PDF, otherwise, once every, once every 32 times, it's pretty uncommon just to see exactly this pattern. We're looking for exactly that pattern. And if we see those bits, then we generally, what we can start to do is then interpret the rest of this file as a PDF or an MP3 or a PNG or a GIF or a so on and so forth until we encounter some other signature that we've reached the end of that. So sort of bookending those two parts. Whether that's a whole bunch of zeros at the end or some other signature that's again perhaps the start of another PDF or another file type altogether. So it is possible that we could end up with like a false positive. For example, anything, if you're looking at perhaps this in the future and say like my hard drive failed and I happen to literally have the characters %PDF typed into this slide, into this PowerPoint, like if you were to go through this PowerPoint slide and forensically recover my hard drive and then you were able to then analyze and say, oh, well, in this particular file, I'm presenting the slides to you and then in the slides you literally saw the characters %PDF in, as ones and zeros, you might mistakenly think, oh, okay, well, this happens to be PDF and then start to interpret the next slide and anything onwards from this particular slide in PowerPoint, this yellow point onwards as a PDF. And it wouldn't work, of course, and that's okay. Like, it wouldn't make sense. You would somehow get a false positive sometimes, and then you might just disregard and keep looking, perhaps. You start looking for a different kind of file. You look for a different kind of file signature and so on. But it can happen that you at least have a false positive like this in situations where you're trying to sort it out because you have no other context clues. You're really working with raw data, and you have all the bits and all the information that you know about file signatures, but that's what you pay people to do, essentially. Okay, so we have this empty trash, so with this like recycle bin, you might as well on our computers nowadays, but we now know, we've agreed that it doesn't actually empty the trash at all. Like, how do we actually delete files? How do we really wipe a hand with hard drives as opposed to just having our hard drives forget our systems, or having our systems forget where they are on the hard drive, where the file actually lived to begin with? Well, what we want to do is, at some actual point, we want to get rid of the data on our machines. How do we go about by doing this? Well, there's actually a relatively few different ways that we can go about by really deleting this data. And the first of which is, we kind of already discussed, which is basically destroying the hard drive itself, throw it into the fire of Mordor. There are services out there, people you can pay, that will shred your hard drives for you. And again, if you need your read-write arm breaks in a catastrophic way, well, your read-write arm will shred the device itself for you. That's one way to make sure that your data is protected, at least, just to make sure it's absolutely impossible now to recover information because of physical destruction. This is a cool video, which I can load, cool, called a degasser. Degausser completely destroys all data on magnetic hard drives and tapes in less than 45 seconds. The TS1 is NS. I'll just maximize the video if you don't mind. Okay, so this is an official documentation. It's a bit boring, but just to get the image in your mind, it's all these things and more. This is what the degausser looks like. You will put your hard drive inside of it. Not only will it wipe out the information by resetting all of those bits, flipping the polarity of all those bits from north to south and south to north or something like this, but it will actually usually cause some kind of mechanical wear just based on the strength of that magnet. It will screw it up, let's say, okay? Okay, takes an image. And it's now gone. All right. Yeah, good luck trying to recover that. All right, cool. And then that's just a promotional video from there onwards. So that's your hard disk drive wiping, okay, using a degausser in that case. They're pretty cool, they're very tough. But then we have this other thing too, and you might find this too in your machines, which is secure empty trash, rather conveniently underneath the option. We saw this in the menu a second ago. What do you think secure empty trash does? Well, one thing that you would think is that it would again overwrite the data with random bits, and you'd be correct, it would. That's what secure empty trash does. So instead of deleting information from the hard drive by forgetting where it was, instead we actually go to that spot, and instead of writing all the ones and the zeros or ones, we just scribble over it, okay? We just write rubbish, essentially, just random bits into it. But it turns out that even that's not actually good enough to delete the information on a single pass, because a single pass is actually what the secure empty trash does. It only makes one pass through, one randomly setting all those, each bit of that file to 1 or 0. And if you know anything about computers, is that there's no true sense of a random, and it turns out that, and the physics of this is beyond me still, I don't know, but it turns out that when the polarity of a magnet on a hard drive is actually flipped from a 1 to a 0, when you do that on a magnet, there's actually sort of this lingering halo effect that it leaves behind, so that you can tell, well, this bit is a 1 now, but it used to be a 0. And that effect lingers on for some little time. And again, if you keep changing it multiple times over and over and over again, that effect eventually gets lost. So you can tell what bits, imagine every bit was a 1 after you make one pass through it. So everything turns into a 1. And all of those things that were ones before, their polarity didn't flip over. Well, then there's no halo effect on them. But everything that used to be a 0 and now is a 1 does have this slight signature left behind that says, I used to be a 0, now I'm a 1. And a good forensic analyst would be able to take a look at this. with some specialized tools, as it reads, it can read the polarity of a magnet and see, well, it's not exactly 0, but it's not exactly 1. It's a little bit off. It's okay, this bit probably used to be the opposite. And you can kind of, under a microscope, tell the two apart. So the point being that just making even one random pass over across a hard drive, one hard disk drive wipe alone, is not actually definitely good enough to securely really erase all the data. There is still one last hope. You actually do have to make it's considered to be 7 passes in the industry to make sure that there's enough randomness, there's enough noise in the answer to have affected each of the individual magnets at such a degree now that you really can't tell what was there before. No one can. So once you start to get into the physics of it all, just to truly securely eradicate the hard drive once and for all, just to preserve it in a state where you can actually use it now for good, which is, by the way, what happens every time you use an EBS volume. They will wipe it 7 times over. You need to use, again, there are software tools that do this. There is a tool to overwrite your previous consumer's EBS volumes to randomly multiple times in order to eliminate any lingering effects thereafter, any halo effect, okay? But again, just for our concern, secure anti-trash doesn't do that. It only makes one single pass over it, but it's just enough for it to be indistinguishable to understanding eyes. But experts who would study this, people who are experts in the field and work with this kind of data regularly, they might be able to figure this out if their skill is, to figure out what the original data was, if it was just one single pass. But that's getting into corner cases, okay? Why is this important? Oh, okay, well, 2 reasons. One, as architects, as consultants, as maybe specialists, we want to make sure that what we're doing is doing everything we can do to protect our client's data. If we're consulting, we have to do it with the best in mind. And also, again, if you're working with people who are less technically inclined, it's also important for us as part of our competent representation of our clients to inform them what we can and what we do know about the technology and the implications of using technology and some of the things that they do from, again, a security perspective. Okay, that's what these sessions are for. And so if you're working in a large firm, in an environment or sort of an in-house council, perhaps, it's probably not going to fall onto you specifically, you individually, to develop some kind of a protocol or establish best practice for working with client data. But it is useful to understand or appreciate what the protocols are, how you might be able to contribute to at least have a conversation about what those protocols might be, okay? That's what we're doing here. And so, wiping our hands now, one of the most basic things you can do, just you as a consultant, as an architect, to protect your own consultant's data, but also to advise people on how they protect their own data at home and so on. Well, the first one's quite easy, just to encrypt your hard drive. So we've talked about encryption already, but you can actually encrypt your own hard drive, such as that when your computer turns on, all you need to do is enter a password. Okay? When it's non-powered on, essentially, everything's encrypted, full at-desk encryption. So again, similar to this public-private key idea, you need to type in a password in order for your entire hard drive to be unencrypted, such as that you then can read the data on it. Most operating systems will now give you tools that are built into the firmware itself to let you do this. So there's no excuse not to do this. Okay, I think it's by default nowadays. It's already on, straightforward enough just to make a pretty strong step of protecting the data in your machine easily. So that at the very least. Again, this will require a password from us typically. So that might be after you turn your encryption on, your computer on perhaps, or before the operating system itself loads up. So the operating system being one of the few things that's itself not encrypted, such as that your operating system itself, something has to load, open the files and unencrypt everything and so on. But it will not proceed. You can't do that initial step past the operating system until that password itself is provided, until you unencrypt the full hard disk drive. But just be careful, because those systems, particularly the most advanced ones, after a certain number of incorrect guesses, will begin to securely wipe your hard drive because the machine is stolen. Again, using multiple passes, ones and zeros. So if you think that there's a danger, if you work for the MI5 or something, if you might forget your master password, perhaps, so to speak, for this hard drive encryption, you might want to keep something somewhere just to remind you. I wouldn't recommend having a sticky note on your monitor or anything like that, but just have some way of remembering the password in the event that you might forget it, because you might lose data if you guess wrong too many times, depending on which hard drive encryption you're actually using. That's a bad thing. Another simple thing for us to do is, again, avoid using insecure wireless networks today. This it's just generally not as common nowadays, but most people have wireless connections that require a password. Okay, Wi-Fi usually would require a password for you to that will then have encryption in order for you making that connection on that system on the network. But again, I travel to Spain a lot, and then everyone in Spain has every bar, every street and every road in Spain has a bar, and every bar in Spain has an open network on the Wi-Fi. So very tempting, to go on these unsecure networks, but they do present opportunities for those rather savvy amongst us to have listening tools on these networks using what's called as packet sniffers. And I've seen them. I've seen these, personally. They're literally just listening and gathering data on all the packets of information that have been transmitted over the internet in the vicinity of that unsecured wireless network. Wireshark amongst them. But it's even smaller than this. Folks, if you are interested in this kind of world of the deep web, Jack Resider, let me just link him up. There is a phenomenal series called Darknet Diaries. He is a podcast, he's a journalist. He does have a lot of interesting people come on and talk to him. And I find it very interesting. Anyway, I'll leave that for you to have a look at. Some of the better ones are there, especially when it comes to, right here, for example, the most played episodes. Yeah, I really like this one of the Pirate Bay. Well, they get one of the founders of the Pirate Bay to talk to. Anyway. One of the most recent, I think it was this episode, I went to bed listening to last night. This guy, MG, he was the guy behind the rubber ducky. If you're familiar with the USB stick with the exploding device inside. So the OMG cable. So it looks to me like a regular cable, but inside of this, there's actually a keylogger that will know everything that you've ever typed. And the one that he developed onto also has the rubber ducky inside of it, which will then explode and then possibly ignite a fuse to then blow up. So it can actually harm the device physically by essentially lighting a fuse and then blowing up, putting a bomb into it, okay, is what I'm saying. It's possible to do nowadays with something indistinguishable from a real cable. Crazy. So these are the kind of opportunities where if you are, I'm not saying that it's going to happen to you, but if you are the target of phishing or spear phishing, that is when someone really does the research on you, then they can get into your mindset. Yeah, Nick pointed out this is Wireshark. This is exactly that. So this is a screenshot of Wireshark, although a little bit blurry perhaps. A lot of relevant information on this, but again, using a unsecured network, HTTP, it is possible for us to read all the bytes and all the bits that are flowing through this and translate them into your ASCII equivalents and realize, oh, well, this person here just types in the username, they types in the password, and then press an action, they've logged in. And so anyone who's listening into this using, again, an unsecured network type like HTTP is then able to grab this information from the airwaves and then literally see what's that IP address, where did it come from? And we'll talk about IP addresses shortly as well, but to see where it's going to as well, might be able to use that data in order for us to log in as that person, essentially perform a machine in the middle attack or a man in the middle attack, which would definitely not be a good thing as well. So again, one way to get around this, I guess, if you're in a situation where you would need to connect to the internet and you do work for whatever reason, you need to be connected to this unsecure internet, if you have to, if you know the way around this, even if you're not sure about the quality of the network, it's just to rely on like private or work provided VPNs. So a virtual private network, a VPN, gives you a way to connect to a trusted encrypted network, have that network act as you effectively, and then provides encryption services for your web traffic, puts a shield around you, so to speak, so that even if you're not sure that your traffic itself is unencrypted, VPNs are available, as most businesses, as most of they're ubiquitous nowadays, relatively inexpensive and even free as well. But you can buy tools that would allow you to make use of that VPN. And password managers, please, they're great. Honestly, I can tell you that I don't know my own passwords. I have made 2 passwords today. I don't know what either of them are because I rely on a password manager. I rely on a few services out there like LastPass, OnePass, and others too. I use one called NordPass, but essentially the tools will generate a password for you. You only have to remember the master password, the one password to rule them all, one password that you can then unlock everything to then open the password manager itself. So better yet to have one kind of centralized strong password to remember. And then once you're logged into the password manager, you then directly log into on behalf of all your different services. You literally tell it, well, this is the URL I'd like you to go to, this is the username I'd like you to use, and then the secretly generated password so that you don't generally now need to know, is it stored in your password manager itself. So some of the tools are going to be local to your machine. Most of them, often rather than not, they actually started to appear as more like cloud-based services. They might appear as plugins and the like. So again, this would introduce another interesting question, like, do you then trust your passwords to be stored in the cloud, stored on Google's cloud, as opposed to being stored on your device? I guess that's another question that you should maybe think about when trusting those tools. But trust is going to happen at some level, either trust yourself and the shortfalls and pitfalls around this, or trust upstream. But again, most of these tools will have a secondary effect where they will often provide a 2FA, two-factor authentication. So 2FA is something that, again, I think we know by now, we will talk about again, but it's something that you know, like a password or something that a password manager knows on your behalf, something that you have, like your phone, for example. It might be getting a one-time password, a code, which is supposed to enter as well. The idea is that an adversary who is trying to hack your account, be you, they may know your password, but they won't have your phone. Or they may have your phone because they took it from the table, but they don't know your password. So they don't have the 2 factors. And those 2 factors are designed to preempt just basic hacking attempts there. Like I mentioned, these tools are great, but they're not perfect. Be skeptical, have a healthy amount of paranoia, because particularly if they're cloud-based, because it is possible for bad things to happen up in the cloud too. For example, not so long ago, a few million users of the password manager Blur, goodbye Blur, they don't exist anymore, they had information that was leaked online. Again, none of the information that was actually passwords, it was more customer rights information like, sort of ancillary, their email address and other stuff too, but it hits a little bit harder to home, So again, always be skeptical when you're thinking about your own data, into your own client's data too, if you're protecting, because those tools are they're more generally good than bad, but again, the decision of whether to use these tools does ultimately fall to you, having done your research into them and picking them for a reason, seeing whether or not they make sense to you, and again, that's what a good architect does, whether or not to take advantage of the advantages that they do offer or not, okay? Again, if you're not using a password manager, at least minimally try to be using a complex password. Certainly try to make avoid using the same password for multiple services if it's usually like a throwaway password that you use on things that you don't usually care about because you're prone to things like credential stuffing. But you definitely want to avoid using the same password on important things. So like your Gmail account or any work-related information that you have or anything banking-related. You definitely want to use different passwords for those things too, because passwords that have less than 8 characters or less than equals to 8 characters, you should effectively consider them having already been broken, consider them already being hacked, okay? Because they're not secure. Computers are definitely power enough today, especially, that it can just brute force their way in. So with a relatively short amount of time, anything that's 8 characters or less, we're still maybe talking days here for an 8-character password. That is definitely not that much effort, okay? Try to be at least 12 characters for sure. It's really important. You definitely have a mix of uppercase and lowercase, numbers and symbols and things like this. Just anything that is less than or equals to 8 characters should definitely be considered now effectively hacked already. If it hasn't already been hacked, certainly it is capable of being hacked very easily by anyone who puts in the brute force effort to do so. So we don't want to be, stale, so change passwords as frequently as you can. Like, for example, I have a bank that needs me to change my password every 90 days in order to keep using them for their online banking. And on the one hand, yeah, that's kind of annoying. But on the other hand, it's kind of a good thing to keep changing things so that I never have my password get stale, potentially leaving it vulnerable, especially the password if I've used it in multiple services and things like that. It's just a good thing to keep in mind, especially if you don't have that many passwords that you need to maintain. Just change them as frequently as you're able to, okay? And make backups. Backups of information is really, no one likes it, but everyone cares about it when something happens because things will go wrong. Account for failure. It's something that you don't expect. like your hard drive will fail, you will suffer some kind of catastrophic mechanical failure. You wouldn't otherwise have a way to get that information back online. You accidentally fell into a chaos machine. So periodically backing up your data, protecting the event of hardware failure, or in the event of some kind of ransomware attack, perhaps where a hacker breaks into your network. Could happen in many ways, and they don't actually take any data. They don't harm your device necessarily, but they do encrypt it using their own public key and their own private key, such as that there's no way for you to read that information from your own machine until you usually pay up some kind of ransom, usually money or Bitcoin or something like that. So for that reason, our defense is having our backing up as best as you can. Back it up in the cloud, put it in a bucket, put in some cloud-based document storage, back it up on paper too in situations as well. But definitely back it up to non-networked connected machines. Okay, so a computer that you have that is never connected to the internet, perhaps like an old laptop, it's primarily used like a hard drive, perhaps, basically, or to flash drive, to CDs, if you're still using CDs. Just have it offline in a Glacier-like vault. That's what Glacier is. It's just offline storage to access in important data in such a way that in the event of something going really, really, really wrong, you at least have that idea. Plan for archiving on the topic of Glacier, like you don't have to keep data around forever necessarily. Like I often think that because we're living in this digital world where everything we do persists forever and needs to be persisting forever, and it's kind of tracked, but it's not really true. Particularly if we're proactive as doing our part to achieve or archive or deleting data when we're no longer needing it. Don't pay for it, don't need it. So, particularly if you're considering client data, if you're consulting for a company, develop a plan for them. So when you finish working with that data, for example, it might be the case that in your firm, after 3 years of no longer having any matters related to your clients, it's just your office's policy to delete that data forever. So you're done. So that might mean us transferring data to a shared disk, with them maybe off of it, and literally going through the process of either destroying the data, giving them the multiple passes over, the ones and zeros, just to obscure that data, just to sign off and having that policy of not keeping things around forever. It generally protects you. It protects your clients too, if that data is no longer needed. So, empty hands. And I guess, just game days, talking about data security as a priority. I know it's not the sexiest conversation to have, especially on a Friday night, but a lot of people are not as thoughtful about technology as you are, as you're taking here this course. So it might be a shock to them just to realize that when they delete a file on the machine, it doesn't actually do anything. Basically just forgets that information, but that information lives on. That probably is not as common as we now know it is to be. So you don't have to be a tech expert to educate others. Particularly as someone who's coming into this with maybe a little bit of, a leg up in understanding technology now, speaking to individuals who may not know anything about what technology is, you can really do yourself and you can do others, your clients, your colleagues, do them a service by making this part of your conversation, okay? So just share your knowledge with others in your field and talk about that too. I think finally, establishing a compliance protocol too. A lot of the things I just described in a very, very, very easy way to set up at the outset. That's pretty much done by default. It's not difficult to say, like, I'm going to change all my passwords, I'm going to use a password manager, I'm going to write this policy for deleting information and archiving information periodically. But the problem is that it becomes harder over time. It's something that we forget to do. Having regular periods of just having someone designated to make sure that those policies are being followed is really important, as, we'll see when there are kind of ethical requirements of having us deal with technology. So you want to make sure that if you establish some of the ground rules for working with your data, that you continue to follow these rules as you start to work with your data for the months, for years, and so forth going forward, because as opposed to just doing it once and forgetting about it, walking away, technology is not static. It's going to continue to advance. It's going to get better. So we need to stay ahead of that as business people. And it's part of our obligation, really, just to understand the technology, just to stay current with changes, to adapt, to change our policies accordingly, so that we're always staying as close to the cutting edge as we possibly can, as individuals. And so I would encourage you to volunteer with the compliance team if you you may have a compliance team, and particularly if you work in a big space, in a big office, in a kind of a council setting, who is tasked with developing these policies. And even if you don't feel like you want to advise on new avenues or pursue new policies to initiate, you should still be part of that conversation. You do bring something to the table just by having knowledge that you get from a course like this, just so you should be part of the conversation that you can then contribute back to for more in the future as well. So I guess I'd just like to finish our discussion today and walk away by drawing your attention to some important ethical discussions that do relate to technology and what we should do in the event of a data breach in their office. And so just wanted to have a look at the formal opinions which were released again in the DPA for 2018. That's the Data Protection Act. That's the UK's primary protection. So our legislation, it works alongside the UK GDPR, and that gives us the legal basis of how personal data is going to be handled in the UK. So after Brexit, the EU GDPR, that was, again, it was retained, it was then tidied up, it was adapted for UK law. So now it's called the UK GDPR, and the DPA kind of does fill in the blanks here. It adds details. It deals with things like the things that the UK GDPR doesn't necessarily cover, like law enforcement data, national security, things like that. Obviously, it's a very, very long read. It's not all of that interesting, but just with respect to the technical know-how, still, rather than just waving our hands at the solutions and shrug it off under the umbrella of compliance, and I thought we just understand what that really means. Suffice it to say that just saying the word compliance doesn't really cut it for the real world. Like, we say this between ourselves, it's now, I think, considered part of a competent consultancy, for you as an architect to actually be considerate of the technological implications as to what you can do in an office. And so this is one such place to find that answer to your questions, like what does it mean to store data? What does it mean to store documents? What does it mean for secure communications with clients? It's now incumbent upon us to stay abreast of all the developments and really just be informed about them, and just inform the clients who we work with about the ramifications of some of the things and the advancements there too. It also formalizes, again, what do you think about when you receive client data, when you work on client data? Like, this opinion came out some years ago. It brings up a discussion here. So I'm just reading. how do you deal with a situation where you have a client who doesn't want to use secure communications or doesn't want to secure the data that's working with you? Like, how does that square with your job or your requirement to ethically abide by this opinion of theirs and just be mindful to guard clients around mistakes? Technologically not best practice. Is it possible for you to still technologically consult for them to give them representation if they are unwilling to adhere to your compliance protocol? What's going off? Sorry. Again, like this is an answer to a question that I don't have an answer to, but it just gives you a discussion about what does it mean for us to have a client intake and work with clients, and what happens if the client's wishes are against our own firm, our own obligations. It's not. That's not a novel question again to consultants. It just presents itself in like different ways by technology. We have another way just to consider the dilemma. Okay, if there's a data breach of the office, okay, if your firm has data that's leaked, it's compromised somehow, like what do you have to do? If one thing to think about here is that opinion formalizes the notion that there is this sort of long held in circles that, there are two kinds of businesses that exist, ones that have been hacked and ones that will be hacked, okay? Now, the ones that might not be ones, or ones that could be, perhaps even those ones that have been and don't even know it yet, okay? But it's such a part of life nowadays to be hacked that, businesses either have been hacked or will be hacked. That is just a mindset that you should have when you're thinking about protecting client data too, okay? Bringing in consultants, being as architects, hiring people to do their best work to defend against your client's data. Now, as it turns out that if you start to consult, if you consult for public services, like firms tend to be excellent targets for hackers, and the reason is that they have a lot of very valuable data. Like, unfortunately, the history is such that it's not always the best protected by public servants. It might have been by the clients themselves, perhaps, because we as architects now, we as technological consultants, we have now been equipped to have a conversation about technology and how that technology might affect the representation thereof. But just again, going to this website, we'll have a whole bunch of different cyber episodes, so to speak, that might comprise a data breach, which would then rise to the level of needing to report this to them, to include things like ransomware attacks, like we discussed a bit earlier today. So system attacks where they might somehow break or damage the infrastructure you've got in the workplace. Exfiltration, so probably the worst kind of breach where someone hacks into your system, is able to remove the data, kind of steal your data such as that you might not have a copy anymore. And that's why, again, having backups is such an important thing, because that removes the data from your servers, into your adversary servers. So, by the way, there's no ethical... It is not a crime to be hacked. There's no violation in that. It's just to make this clear, the ethical violation it has when unreasonable efforts have been made. Like, if you make unreasonable efforts to protect that data, if you're making reasonable efforts to protect your data in the first place and you still get hacked, you have not necessarily done everything. Like, you've done nothing wrong as long as you've done what you could have done to prevent or protect that from happening in the first place. And once you detect it, once it has happened, make every reasonable effort to stop the attack if it's ongoing, if that's the case, okay, from continuing. Yeah, so just looking at the time, I think who owns the data is often, part of that conversation here. Generally, as we know, we would return the client data back to them when we've done work with them in the consultancy. Like, how does that work digitally? That's also part of your intake plan that your firm to handle what happens to your version of your client data, what the representative, when is it concluded because the matter is ended, and you kind of wipe your hands with that too. Speaking of concluded, I think wine, folks, that is going to probably wrap up our discussion on security today. This will be the first of two discussions generally at this level of security in our context in memory and hardware. Next week, I'll talk about this more at the network level, but hopefully you come away today with hopefully a better understanding of how your system works, what memory is, and why when we delete things on our hard drives, it doesn't actually get deleted, and what some of the implications of that might be. Hopefully you come away from this, just a better understanding of what to do going forward, establishing best practices, work with your clients, and how to stay, ethically in the guidelines, okay? Just to generally have more of a conversation with people you work with about your representation of them and what happens to be the data when that has been finished. Yeah, so we'll see you very, very soon, folks. Nick, Anka, AJ, Manpreet, Chantel, Dennis, Marceli, Mohammed, two Mohammeds, and folks too. It has been a pleasure. I will catch up with you very, very soon, and have a good one, folks.